Hello and welcome to ML with AP. The topic for today is decision tree. Decision tree is a supervised learning algorithm which is used for both classification and regression tasks. We are going to see both the uses of decision tree. Let's learn. But first thing first, what is decision tree? I just mentioned that decision tree is a supervised learning algorithm which is used for both classification and regression tasks. But let's try to understand it intuitively, what it means. And we'll try to understand this with a small data set. This is the data set. The data set is very simple. It has 4 features. The first 4 columns are the features: outlook, temperature, humidity, windy. All 4 are categorical. The last column is my y variable, or the output variable, predicted variable, is play golf. So based on these climatic conditions, we have to predict whether somebody would like to play golf or not. This is the data set, right? Now, this particular data set, if suppose somebody comes with a requirement or a prediction that, hey, can you give me a model which will give the prediction on if the outlook is rainy, temperature is hot, humidity is normal, windy is false, whether somebody would like to play golf or not. Can we build a model? Right? That is the question. Of course we can build a model. We can use any of the classification algorithm which we have learned till now. We can use logistic regression, we can use SVM, we can also use neural network for that matter and solve this issue, right? But there is another algorithm which is called decision tree, which is also very good, and we should also learn about it. Now, if I have to say decision tree in one word, it is nothing but a giant rule of if-else statement. Why do I mention if-else statement? We'll try to see that in a moment. This is how a decision tree looks like. If you are coming from a non-computer science background, this would look little weird to you. This is actually an inverted tree. If you see, the topmost is the root and the bottoms are the leaves. In a natural biological tree, it's the other way around. Root is at the bottom, the leaves are at the top. But over here in computer science, it's the other way around, right? This is a tree. This is a decision tree. Now, if you notice this decision tree, my first decision I'm taking is that whether the outlook, if you see the play 9 and don't play, these are the observations. So I have 9 observations where I'm playing and 5 observations where I'm don't playing. Now, based on outlook, whether outlook is sunny, overcast, or rain, I'm further splitting it. This is nothing but if sunny, play 2, don't play 3 observations. If overcast, play 4, don't play 0. If rainy, play is 3 observation and don't play are 2 observations over there. If you read this, let's say on the right side of the tree, it reads like if outlook is rainy and windy is false, play, because the don't play observation becomes 0. So this becomes a leaf node over here. The majority class is for playing, not don't play. So my vote will go, or my prediction will go to play. That's the reason why I'm saying, friends, that this is nothing but a giant rule of if-else statement. Again, repeating, if outlook is rainy, if windy is true, don't play, right? Don't play will come to 2, right? So this is in a nutshell what decision tree is. Now we'll try to understand how to build that. It looks very easy, nice and clean, but how to build that? There is a science behind that. We'll try to learn that. Okay. Now, to give you the example, what we wanted to predict was if it's rainy, hot, normal, and false. If it's rainy, the red arrow. If it's false, okay, windy is false. We are not using the use of the middle 2 features. Then I should go and play. My prediction will be play, right? Let's try to understand few of the nomenclatures before we dig deeper into decision tree. As I was saying, the root is at the top, so it is called root node. The other, whether it is windy, true or false, outlook is sunny, cloudy, that is called decision. So after root node, there will always be a decision node. Decision node is nothing but where we are branching out, whether we are making a call, whether it's true or false, less or more, greater than or smaller than, right? We are taking an if-else statement over there. That is the decision node. Similarly, this will keep branching out, okay? The portion where it stops branching out is the leaf node, right? is the end of the tree is the leaf node. Now there can be multiple leaf node, but there will be always be one root node, right? This whole thing is called a tree, and a similar structure is called a subtree. So if you see in the dotted, this is a subtree. On the right side also, this whole thing is a subtree. This particular thing, anything which is decision node and everything beneath that can be termed as a subtree. So this can also be termed as a subtree. This particular whole thing can be termed as a subtree. So this is the right subtree for this root node. This is the left subtree for the root node. Now we understand what is root node, what is decision node, what is leaf node. Let's move on. But there are a lot of questions. We understood that, okay, how intuitively decision tree works. It's a if-else statement and all those things. But how should we build the tree? What should be my root node? As I was seeing, there were 4 features. Which feature I should pick for my first decision node, right? At the root, at the very root. How we should do the split, right? If there is, let's say outlook is sunny, windy, sunny, cloudy and rainy, how should we do the split? Again, if we make the root node, how should we make the subtrees? What is the logic for making the subtree? When to stop? Do we always need to go to the leaf node? How we'll know that we have reached the leaf node? What is the criteria to split? What if we have a continuous feature x? So if one of the feature or many of the features are continuous variables, right? Instead of categorical, which is sunny, cloudy, rainy, if suppose it's a number like temperature is not given between high, medium and low. It is given like 17 degrees centigrade, 24 degrees centigrade, 13 degrees centigrade. That's a continuous variable. So if my feature is continuous, how should we deal that? What if my output variable y itself is continuous? What will happen then? If my output label is continuous, that means it becomes a regression problem. So rest all the things are related to classification, which applies as well to the regression setting. But the last question specifically, if you are asking that, hey, what if my output variable y is continuous, it becomes a regression problem. Let's try to answer each of these questions and understand decision tree in greater detail. Let's see the first question. Let's see how to build a tree. So we have 3 principles to build a tree. One is recursion. We recursively build the tree. By that what I mean? By that what I mean is, let me show you. So we build the root node. We do a split over here. Okay. To build this particular tree, I will use a recursive logic, what I have done for splitting the root node also. So I'll write my logic one time, and the same logic I am going to apply to build this subtree. For this subtree, it will look as if this whole tree is a complete, this whole subtree is a complete tree in itself. Okay, that's the way we'll do, and that's the meaning of recursion, recursively. What is meaning of top down? Now you are saying that this is an inverted tree, right? In computer science, we'll always look at inverted tree. So we'll start from the root top down. That means start from the root and then branch out to subtrees, further subtrees, further subtrees till we hit a root node, a leaf node. The third thing is, how do we do the splitting? We do the splitting based on the principle of information gain, entropy, Gini index, right? These are big terms. We'll just explain that in a minute, but try to understand at a fundamental level. Decision tree is also a machine learning algorithm, and like any other algorithm, it has to have a loss function which we have to minimize, which we have to optimize, right? In case of logistic or linear regression or SVM or any other naive base, there was a loss function which we are trying to minimize, right? So what is the loss function in this particular case? What is the thing which we are trying to minimize to build the tree recursively? Okay, that particular thing is entropy. Entropy, we are trying to minimize the entropy. We'll just see that what is the definition of entropy, how we measure entropy, but try to understand that this is something, this is like my objective function which we are trying to minimize, or my loss function or my cost function which we are trying to minimize to build the tree recursively. Okay, let's move on. Now, one thing I would like to mention before moving forward is that there are many decision tree algorithms which are available, right? So you will hear names like ID3, C4.5, C.5.0 or CART. CART is the classification and regression tree algorithm. This is one of the implementation of decision tree. Okay, CART is the algorithm which SciKit-Learn package also uses behind the scene, right? So we'll devote our tutorial to specifically talk about this CART implementation of decision tree algorithm. Now, one of the key differences over here is that CART implements binary tree. Binary tree means, friends, if you recall, the outlook was sunny, cloudy and rainy, right? There were three classes. But in case of CART algorithm, which SciKit-Learn implements also, every node will branch out into two. So there has to be a yes no answer, right? It cannot be yes no and maybe or multi-class or multi-label problem. It cannot be like that. It has to be a yes no, greater than 7, less than 7, is present, not present, right? Those kind of situation has to be there. And we'll see that if one of my feature is suppose multi-category, right? So there are 3 categories over there. How can we convert that problem into a 2-category problem? We'll just see that, right? But for the time being, let's understand that we are going to learn about CART, and CART is the thing which is being implemented by Python SciKit-Learn's package, okay, which is tremendously used. But there are other implementations also present in the market like ID3, C4.5 and C5.0, okay. Let's move on. Let's understand this with another example in a further greater detail, right? Okay, this is my data set. The data set is very simple. It has 2 features, x1 and x2 over here, and 1 y variable which is loan approved. So this data set is that whether the loan should be approved or not. I'm building an application which will predict the loan should be approved or not. And this is the feature of the person who is applying the loan. So the job, whether the person has a job or not, and whether the person has a house or not. Based on these 2 simple criteria, categorical criteria or features, I'm going to predict whether the loan should be approved or not. Very straightforward data set, and we'll try to implement decision tree based on that. Now we can always convert this into 0 and 1. Since this is a binary, my binary classification, my y is also yes or no. There is no maybe over here. And if you notice, my job and house both are binary categories, right? So either true and false, yes and no. We can easily convert that into numerical 0 and 1, right? Okay. Now let's see, if you recall, our first challenge was, hey, how do I select a root node? Now, if you notice, here is x1 and here is x2, right? So we have 2 features over here, right? Job and house. Which feature or which decision should be my root decision, right? That is the question. And now once we understand that, then recursively we can build rest of the tree also. Now let's try to understand how the first split happens, the root split, how that partitioning happens. Let's say what decision tree says is that you try to do the split on both of them, right? Both of them are a candidate, the job and the house. We'll try to split on both on job and house, and we'll try to see that what's happening. Okay, now the first decision was, or the first point of a split was, has a job x1. So total, how many features we have? 15 features. How many yes we have? 9. How many no we have? 6. In case of house also it will be the same thing because we are at the root node, right? Now let's see. If I'm splitting on the base of job x1, right? Job is there or not? Job is yes. That means this feature, this feature, this feature and this feature, right? These observations, sorry, if I have these observations. Now if there are the observations, how many observations are there? 1 2 3 4 5 yeses. How many total? If I do yes on my left side, on the yes side, how many observations fall? 5 observations. How many yeses are associated with that on the y side? Yes, 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 yes. Apparently everybody who has a job gets the loan approved, right? So my yeses are 5, my no's are 0. On the right side of the split, because it is a binary split, right, there will be a left side and there will be a right side. On the right side of the split, let's see, no, 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 right? So overall, we have 5 observations went on the left side, 10 observations come on the right side with no, right? Out of those, how many yeses are there on the y side? 4. How many no's are there on the 6, right? Similarly, we'll split this also. Now you will ask that why we are doing this split. Now, just wait for a minute, and before, let me explain this. So let's try to see again, I'm repeating, how the split is happening. Split is happening, both are candidates. We are trying to split on both of them, and out of these two, we'll select one split, right? Either job or house, because we have 2 features. If we have m number of features, there will be m number of candidates, and we'll try to do this exercise for all of these features, right? And how we are doing this exercise? We are trying to split this into yes or no, or it could be like low or high, whatever be the category. We are trying to do the split, and then we are counting the number of, in each of these buckets, after the split, we are counting the number of how many total observations were there, how many of those were yes, how many of those were no, right? This is based on the y predicted, y variable, right? This is what we have counted till now. Now, if I ask you that, hey, should I do the split on x1 or x2? Which one is better? There is no way of clear knowing that, right? We have to quantify this information that which one is better. Intuitively, it makes sense that, hey, looks like this 5, 0. Okay, this is a cleaner split, right? Cleaner split. What do you mean by cleaner split? That means over here comes the concept of entropy. Entropy is a concept which came from physics, but in machine learning and computer science, it is used in information science as well, and it says that the amount of impurity present in a particular data set, right? What do you mean by impurity? Let's try to understand that. Let's try to see this particular picture. So there are green circles and red circles. The first picture is saying very impure. Entropy is very high in the first picture. Why? Because it's like half is the red, half is the green balls over here. This is less impure. Why this is less impure? Because if you see, the red balls are very less compared to green balls. Okay, this is almost pure, or actually pure. This carries the minimum impurity. Why? Because there is only one class which is present. It either red or green. If only one class would have been present, this is called minimum impurity, or almost pure, right? This is the concept of entropy. In this particular case, it's very impure, highest entropy. This less impure, medium entropy. This is low entropy situation, because only one class is present. If there is a mixture of both the classes in equal quantity, that is the very highly impure situation. This is the concept of entropy. What is information gain? We'll just see in a minute. But first thing first, how is entropy calculated? And entropy calculated for categorical variables. How is entropy calculated? So this is the formula for calculating the entropy, right? Now this formula may look complex, but let's break it down one by one. Okay. So the formula says if there are C classes, right? Now our problem is always binary classification, right? We are splitting into 2 parts, right? Yes or no, because our just for the understanding, let's say that we have binary classification. In that particular case, if we have to, C will become 2. What will this thing become? This thing will become minus P positive class. 1 is representing positive class. So minus P log base 2 P1. Again, for my negative class, it will be minus P0 multiplied by log 2 P0, right? This is the formula for entropy in case of a binary classification will be, right? Now in case of binary classification, friends, you already know that P0 will be 1 minus P1. If the probability of getting a class, positive class, is 0.7, what will be the probability of getting a negative class? 1 minus 0.7, which is 0.3, right? So this formula also holds. If we input this formula into this, we are getting this particular thing, right? E is equal to minus P1 log base 2 P1 plus, we are just replacing this P0 with 1 minus P1. That's all we have done over here. And this is the formula for binary classification, okay? Entropy. Now, one question will come to mind is that why we are taking this log of base 2 always in machine learning and mathematics we call natural log. Why we are taking 2 over here? Okay, that's the first question. And the second question will come is that if you see this formula closely, it will resemble you to something, right? Do you know where you have seen this? This formula you must have seen in case of logistic regression. If you are doing a binary classification problem for a logistic regression, this formula will appear to you. And that's why we call it over there binary cross entropy laws. If you recall, and if you have not watched my logistic regression series video, please go ahead and watch that. You'll understand that. Okay, so this is called binary cross entropy, and it is used as a log loss function for logistic loss also. Now, coming back to the first question, why the base is log 2? Now, there is nothing essential over here, like we are keeping base as log 2 because the math becomes more beautiful. Let's answer it that way, okay? And why would that be? Let me show it with you an example, okay? So, what I'm doing over here is I have plotted 2 graphs, okay? This is the formula of E, right? For various on the x-axis, right, over here is the probability of your P1, right, on the x-axis. On the y-axis is my E or entropy. If I plotted this like for, let's say P1 is equal to 0.1, 0.2, 0.3, 0.4, 0.5 till 1, if I plot it, my graph looks like this. My blue graph represents the base 2. If I plotted the same thing with log base natural number E, Euler's number, my graph is this, okay? Now, you'll say that, hey, what is the difference between these two? Now, if you notice, this particular graph, which is a base of log 2, hits the maximum at 1, which is a nice round number, matching with the probability, all those things. That's why we are using. And why it is hitting? Why it is hitting at 1? Now let's see, it is hitting at 0.5. Let's put 0.5 over here or half over here, okay? So this particular term will be minus half into log 2 half plus half into log 2 1 minus half, right? This will be the value. If you solve this value particularly, then you will come to know that the value of E which we are getting will be 1. And that's why we are using the base of log 2. Let's see that in an Excel sheet also over here. Okay, so this is the Excel sheet. This is what I was talking about. What I have taken is over here is that my y1, y is equal to 0. If y1 is equal to 0, 1, 2, 3, 4, 5, 6, 7, 8, and let's say there are 10 observations. And for each category, I'm taking that, let's say it is 0, and then my y is equal to 0 will become 10. The reciprocal, because there are 10 observations. If my positive class is 0, my negative class will be 10. Positive class is 1, negative class is 9. Similarly, I have drawn, and this is just to draw this figure. What I have done is, I have calculated the P1. This is by P1, right? How it is the P1? This is nothing but this divided by 10, right? This is my P1, the probability of getting positive class. Now, with base 2, I have done the calculation. If you see, I have done the calculation with base 2. With natural log also, I have done the calculation. If you notice, these numbers are very symmetrical, right? Across this y-axis, this number will be very symmetrical, right? It makes sense. With natural log, also I have done that. Now, if you see, the blue line actually touches at the 1, right? If you see over here, when the probability is half, that my positive class and negative class are equally likely, 5, 5, and my probability is half of P positive class and half of P negative class, what is the value of entropy which I'm getting a nice round number 1. But at the same, what is the probability I'm getting? 0.30, which is not very nice and round. That's the only reason why we are using the base of log 2 instead of base of log e. There is no reason. It is just that it will be a different curve, right? It will still solve the problem, but this looks much more cleaner and beautiful, right? Okay. Now the other thing to notice over here is, let's go back to our slide. Yeah. Other things to notice over here. If you input log 0, if the calculate the value of 0, what will be this particular thing, P1? If log of 0 is actually undefined, right? But for the practical purpose of calculating this, P1 is equal to 0, then log 0, 0 into log 0. So we are considering this whole element as 0, not as undefined, right? So this is a small assumption which we are making to ensure that this is meeting at 0 and 0, right? Over here, at both at 1 and at x-axis 0, our entropy becomes 0, right? Entropy becomes 0 means what? Let's try to understand what this 0 and 1 means. At probability 0 also, there will be only and only negative class. At probability 1, it is only and only positive class, okay? So remember that ball, if there is only negative class or only positive class, what will be my impurity? It will be very purest form, right? And my entropy will be the lowest, right? Because entropy is a measure of impurity. So my entropy will be close to 0 or almost 0, right? So this figure makes intuitive sense to you, right? And you understand what entropy means. Now coming back to our original problem, where we are doing the splitting and partitioning, right? And this is the formula to calculate the entropy. Just remember that for a binary classification problem. Okay. Now let's see what we are doing over here. We are trying to create, using this formula, we are trying to create the entropy. Okay. We are trying to create. Now what will be the P1? Because yes was 5, there were total 5 observations. So 5 by 5, 1 is P1, positive class. P0, there was 0 negative observation or negative class or 0 class. 0 by 5, 0. Similarly, we'll calculate E or entropy for each of these combinations. Okay. So all the 4 I have calculated the entropy, and what I have received? 0, 0.97. Again, entropy is 0 over here because it's almost pure mixture, right? Because it is only one class. Obviously, the entropy will be 0, right? Over here also the entropy is 0.92. Similarly, we have to calculate the entropy for our root node also. So the entropy for root node is 0.97. Entropy, obviously, there were 15 things or observations. 9 of them were yes, 6 of them were no. What is the entropy? We just put it in the formula, we got it, right? 0.97. Here comes, now we have understood what is entropy. Let's also understand what is information gain. Information gain means how much entropy we were able to reduce. The reduction in entropy is called information gain. So entropy at root node was this. Entropy at child node is 0 and 0.97. If we do this particular split, the entropy at root node is 0.97 and entropy at child nodes are 0 and 0.92. Now friends, the question is, our loss function was entropy. We have to reduce the entropy. In other words, what we have to do is the reduction in entropy is also called information gain. So we have to maximize the information gain. That's fine. But the question is, over here, 0.97, one node is 0, one node is 0.97. 0.97, one node is 0, one node is 0.92. Which split is better? Still, there is no way of knowing which split is better, right? So let's try to dig more, right? What we'll do is, okay, this I have already answered, that why log 0, right? If you take log 0, we had just discussed that any base, it is called undefined. But for this purpose, we'll assume that it is 0, right? Okay. Now, we have removed all those, and for all these yellow blocks or splits or the child entries, we have just wrote down what the E which we got, right? We have little more work to do. So pay attention. what we'll do is, what will be the information gain? Information gain is nothing but reduction in E, correct? How we calculate the reduction in E? The E at the root node was 0.97. Then we'll take a weighted average of the entropy at both the nodes, right? That would be the right thing to do. Think intuitively why it would be. Because this thing has been split into 0 and 0.97. Here 5 observations have gone. Here 10 observations have gone, right? We cannot just take that, okay, based on 5 observations, this has become very pure, so let's go with this. No, we have to find a mechanism where we have to give weightage to how the split is happening, or what is the weight of the split also. Suppose there is just one observation here and 14 observations over here. Should we consider both of them reduction equal? No. It should be weighted, because the reduction in entropy is also related to how many observations based on that we are calculating, right? So what we are doing is, out of 15 observations, 5 is over here. Out of 15, 10 is over here. So 5 into 15 multiplied by entropy at this level. Again weight, what will be the weight of this? 10 by 15 into 0.97. This is the total entropy. This thing within parenthesis is the total entropy of the child. And what will be the reduction of entropy? The parent, entropy of parent minus entropy of child. Entropy of parent minus entropy of child, right? Similarly, we will calculate it over here. So over here, if you see, it is 0.32. Over here, it is 0.38. Now you tell me that where the information gain is more, or the reduction in entropy is more. They are both the same thing. Information gain is nothing but the reduction in entropy. The reduction in entropy is more on my right split based on the house. So this will become my root node, because my entropy is, the reduction in entropy is highest at this split. Again friends, if there are multiple features, you have to repeat this exercise for all the features, because every feature will be a candidate for a split at the root level. Which one you are selecting is based on this, calculating the entropy, calculating the reduction in entropy or information gain, and then selecting the one which has the highest information gain or the highest value of reduction in entropy. Clear? So I have to do my base split or the root split as at house level. Correct? This is how we do that. Now, why calculate the weighted average? I think I already told you. It makes sense logically also to do it, because suppose there is just one observation and 14 observation over here. We should not take the average of entropy, right? That will not make sense, because most of the observation has gone over here. So we should give due weight to that particular scenario also, right? Okay, that's why, that's the intuition behind it. Still we have a lot of questions, right? We initially saw those questions that how should we build the tree, what should be my root node. I think we partially answered that. We answered that what should be my root node, right? We also answered that how we build the tree, how we do the split, at least at the base, at the root node, we already know that. How do we build the subtree? These are some of the questions which are still. When to stop? When I reach, how will I know that I have reached the leaf node? These are the questions which are still pending. Okay, we'll see these questions in my second video. Till then, have a good day. Bye.